All right, welcome everyone to our second day of 16.8. Again, we're talking about Stokes' theorem, and this is a little bit about the proof. We're not going to go through the full formal proof or anything like this, but at least give you an idea of the proof of why Stokes' theorem works. So again, here is the statement of Stokes' theorem, and again, this is going to be a quick overview of our pre-class video. I of course did this in much more detail in the actual pre-class video, but just a quick highlight here. We talked about how that really curl here is actually embedding all of our information about circulation. So in the X component, we have the circulation in the YZ plane. In the J component, we have the circulation in the XZ plane. And finally, in the K component, we have the circulation in the XY plane. So this curl vector is really this mega circulation vector. It kind of embeds all of our circulation information. And so we talked a lot about, circulation at a point and kind of extending this to a small rectangle and whatnot. But in general, what we get down to is that when you take this curl dot n, you kind of isolate the portion of our circulation vector that is perpendicular, right, to our surface. And so when you add up all of this circulation, we talked about how that on the interior surface, these are all going to cancel. And the only thing that you're going to be left with is the circulation on the exterior or on the boundary of our surface. And so the boundary of our surface, again, is just this bit right here, right? This F dot dr. Again, this is the circulation. But again, now we're just going around the boundary curve rather than at every single point on the surface. So that's really at the heart of Stokes' theorem, and this is why Stokes' theorem works. It's, again, talking about circulation and just the fact that when you have interior points, that they're always going to have some points adjacent to them, and the circulation will cancel, and you're going to be left with just the circulation on the boundary. All right, so I hope that was some nice insight about why Stokes' theorem works, but let's go ahead and get back to solving particular problems, starting with this one here. So again, we are given this bit. So remember that this del cross F, we got this in 16.5. This stands for the curl of F. So this is asking us to find this flux of the curl. And that's exactly the setup for Stokes' theorem. So again, nowhere in this problem says, use Stokes' theorem necessarily. So you could decide to just evaluate this out as is, but let's kind of draw this out and see why it would be a pain, right? So it talks about that the surface consists of the top and the four sides, but not the bottom of the cube with vertices plus and minus one. So if I was to go ahead and try to draw this out, again, we're going to have a cube with all of the sides and the top, but not the bottom. So again, the bottom's missing. Maybe if I go ahead and shade some of this in. So here's this one side here. Here's maybe a back side. Here's this back side. And here's the front. Oh, and we need the top. So we have the top as well. But again, the bottom piece is missing. So maybe I'll shade that in red or something like that, just to try to emphasize that this bit here is missing. And so if I was trying to evaluate out this surface integral, well, first of all, surface integrals are a pain anyways, but notice that really this surface is comprised of 5 different surfaces. We would have, and each one of them has their own normal vector, right? Because when we go and we evaluate out these surface integrals, we need to dot product with the normal vector. And so we'd have, this surface over here has a normal vector. This one back here would be, a normal vector like that. Here you would have a normal vector going up back this way. This other side would be something going like this. And of course, the top would be a normal vector going maybe straight up or something like this. So we'd, again, have 5 different surfaces, really, and 5 different normal vectors. And so this would be a tremendous amount of work to try to evaluate out these 5 surface integrals that comprise, the total surface that we're talking about. And like this note mentions here that you can apply Stokes' theorem once, and actually there's a WebArc problem that kind of has you explore this. But I think maybe for this one, we'll be a little bit clever, and we can actually try to apply Stokes' theorem twice, and we'll be able to solve it even faster. So let me showcase what this looks like if you were to apply Stokes' theorem once. Again, Stokes' theorem says that instead of, let me maybe cheat using technology just a little bit and move this over for a second. So Stokes' theorem says, rather than evaluating out this surface integral for the curl of f dot ds about some surface, that you can trade this in for a line integral, and the line integral is around the boundary of the surface. So the only place where this surface abruptly stops is going to be along the bottom here. So I'm going to go ahead and try to draw out just the bottom piece. This is the only place, like I talked before, where you can go kind of from the outside of the surface to the inside of the surface. If I imagine I'm some ant or something like this that's walking along the surface. No place else, right? If I was to build this out of paper or something like this, although there are sharp corners, right? And we would, if I was an ant, I would make a sharp corner, something like this, but there's no way to go from the outside of the surface to the inside of the surface by taking this corner. And likewise, if I was to kind of flatten this all out, if I was to make this out of paper, right, there could be continuous paper there. So this is not going to be a boundary of the surface, even though there is kind of a sharp corner. The only place where you have a boundary is going to be down here at this bottom piece, right? If I was an ant kind of chronic along this or kind of across this, right, I could go from the outside to the inside of my surface. So this right here is going to be where the boundary is. And again, you kind of have that all along the bottom here. So rather than calculating out 5 surface integrals, my claim here is that, and you'll see this in web work as well, is that we can calculate out line integrals, which are easier. And we only would need to do 4 of these, right? Because this basically is a square. This is going to be all the places where we have z coordinates are going to be -1, right? Because we had the top, this is going to be where the z coordinates are going to be +1. And then at the bottom, this is where the z coordinates are going to be -1. I didn't really draw my x, y, z axes here. So this could be something like 1, 1, -1, for instance. And then we could have what, like -1, 1, -1. And then this could be like -1, -1, -1. And then this one could be 1, -1, -1, right? So these could be our 4 different vertices, and the z coordinate for all of them is -1. And we'll think about orientation in just 1 second. But again, I want to be a little bit clever in this particular case. And I'm going to apply Stokes' theorem one more time. And I'm going to attach to this curve here a surface. So again, I'm going to be switching back, applying Stokes' theorem a second time. So I'm going to go back to a curl of f dot ds. But now I'm going to choose a different surface. Maybe I'll go ahead and say this is S2 or something like this. And I think a much more natural surface to append to this curve, and so let me go ahead and maybe copy and paste this curve, is if I was to just shade it in. And we've seen this several times now already, that again, kind of the most natural surface that you could attach to this is if you were to just shade all of this in. So rather than appending, some cube, like how we had this to start, right? I think it's maybe more natural to just attach this nice flat surface. This is, as you probably are not surprised, a plane, right? It's nice and flat. It's not, of course, the entire plane. The entire plane would go on forever, but it's just a part of a plane. And it's the plane, we could probably guess the equation. It's where the z coordinate is equal to -1. So again, it's a nice flat plane. No slant to it or anything like this, but notice that the z coordinate for all of these points back here are -1. And so this just has the nice, beautiful equation, z equals -1. So again, part of the plane doesn't, the x and y's are going to be ranging from -1 to 1 sort of deal. So it doesn't go on forever, but it's just a piece of that plane, z equals -1. So this is my idea for Stokes' theorem and applying Stokes' theorem twice. So now notice that instead of having to evaluate out 5 different surface integrals, we're only going to need to evaluate out a single surface integral. And that's going to be much, much nicer. It's even going to be nicer than evaluating out the 4 line integrals, which is still better than evaluating out 5 surface integrals, but not as nice as maybe just evaluating out 1 integral. All right, now let's spend a little bit of time thinking about orientation, right? So if I'm thinking about orientation for this, and thinking about like the right-hand rule, quite often I draw a normal vector that's pretty close to my boundary. And again, I get out my right hand and I have my thumb pointing in the direction of that normal vector. And I rotate my fingers kind of around this normal vector. And again, for my right hand, that'd be something like this. And I imagine kind of along the boundary, there are particles, or really I'm thinking of them almost as like wiffle balls or something like this, right? So I have all of these wiffle balls that are kind of lining my boundary. And I think about if I was to actually, circulate my fingers this way, what way am I pushing those wiffle balls? And I think as soon as I run into the wiffle ball, again with my finger as I rotate it around, I think I'm going to be trying to push these wiffle balls this way. And so that's what way, again, this has something to do with circulation, and the circulation at the interior points cancel, but at the boundary, right, we're pushing these wiffle balls, we're doing work, pushing the particles in this direction. So when we have this outward normal vector, we push the particles this direction. And likewise, you could try to set this up for another normal vector, right? So if I was to go ahead and maybe have a normal vector here, then again, I try to draw the normal vector pretty close to the boundary. And if I was to get out my right hand and spin my fingers around, it'd be something like this. And if I was to imagine, how do I push these wiffle balls, right? I think that maybe, I hope that we would agree that I'm pushing the balls in this direction. So that'd be something like this. And now that's probably enough to guess, that we are going in this, at least when viewed from above, right? We have this counterclockwise direction. And so with this orientation, again, we need to think about what kind of normal vector would we have here. I'm going to draw on my orientation for my boundary curve. And so now, again, I know my normal vector for this surface here is either going to be straight up or straight down, right? That's what the normal vector looks like. And in order to figure out which one this is, again, I'm going to take out my right hand. I'm going to try to curl my fingers in this direction here. And I'm going to think about which way is my thumb pointing. And so my thumb is pointing in this upward direction here. So that's the orientation for this surface. So when I go ahead and I swap this in, I want to make sure that I have this kind of upward orientation for this surface. So let's go ahead and fill in a few more details, and then we can write down exactly what that normal vector is going to be. So the first thing that I need is we're going to calculate out the curl of F. I's, J's, K's, all of our partials. And our vector field is XYZ, XY, and X squared YZ. So again, stuff with I's minus stuff with J's plus stuff with K's. When I cross off that first row, first column, let's see, I'm going to have a partial with respect to y of x squared yz. So I'm going to have x squared z. Subtract away a partial derivative with respect to z of something without z's. So that's just going to be 0. Next up, let's go ahead and cancel out our first row, second column. Partial derivative with respect to x of x squared yz. So that's going to be 2xyz. And I fear I probably have not left myself enough room. Minus the partial derivative with respect to z of xyz. So that's going to be minus xy. And then finally, we need to take first row, third column. So a partial derivative with respect to x of xy. So that's just going to be y. And subtract away the partial derivative with respect to y of xyz. So that's going to be xc. So this right here is going to be my normal vector. Or sorry, my curl. Let's go ahead and write it. X squared z xy minus 2xyz and y minus xz. Okay, so my surface integral looks like this curl of f and then dot a normal vector. So dot a normal vector. And remember, when we have an explicitly defined surface, so that is a z equals surface, a normal vector is going to be given by plus or minus and we take the partial derivative of our equation, our z equals equation, with respect to x, with respect to y, and then our final one is always a -1 there. And that's going to give us a normal vector for any explicitly defined surface. So in this case, if I was to choose the positive, right, and forget about the negative, that means that this would be the vector 0, 0, -1, which means that my z component would be negative. And that's rather alarming to me because this shows that I want it to be pointing upward. And so I'd like to have a positive z component. So what I'm going to do is I'm going to choose the negative option here and choose this orientation. So that way, once I distribute it through, the other ones are just boring, right? You get 0, 0, +1. And now this is an upward pointing normal vector. So my normal vector that I'm going to choose is 0, 0, 1. And again, we have to just think about the orientation for this. I emphasized in our last video, right, that even if you are worried or whatnot that you don't have the correct orientation, my claim is just make some choice for the orientation and see the problem all the way through. Worst case scenario is going to be off by a negative, but especially if these are, these kind of longer problems here are usually standard response style questions, you could still earn, 14 out of 15 points or 13 out of 15 points. You're going to get the majority of the points, even if you have the orientation wrong. All right, so let's go ahead and evaluate out this dot product. Well, those two zeros really help, and we're just going to have y minus xz. And again, now this is a regular old dA here. It's no longer ds, it's dA. So we're doing a two variable integral, x's and y's. And so if I was to go ahead and smush my surface here into the xy plane, it would look very, very similar. But now instead of all those z coordinates being -1, right, they're going to be 0 because again, we're in the xy plane. So let's go ahead. We can shade this all in. This is going to be what? 1, -1. Here we have the point 1, 1, -1, 1, and -1, -1. So I hope, right, you agree that this is a nice rectangle. And so when I'm choosing how do I want to integrate this, and I can integrate either with respect to x first or with respect to y first, or in polar coordinates, right, that hopefully you disregard polar quite quickly. This isn't anything circular or whatnot, so let's stick to rectangular coordinates. And then it really doesn't matter if I want to do y first or x first, so I'm going to go ahead and just choose that I'm going to do dy dx. But then this gets us to the last bit, right, that when I'm integrating with just x's and y's, the fact that I have a z here is rather alarming, right? And now I need to swap that in, feasibly for, so that I don't have any more z's left. And so again, when we're on this surface, right, z is equal to -1. And so that's what we're going to go ahead and swap in here for, is instead of z, I'm going to put -1. And so now this -1 times this -x, that's just going to be really y plus x here. Y's are going to range from -1 to 1. X's are going to range from -1 to 1. So this right here is our setup. Let's spend a little bit of time evaluating this. So when I integrate this first with respect to y, I'm going to have 1/2 y squared plus xy. And we need to evaluate that from -1 to 1. When we do that, let's see. 1 squared is going to be 1, minus -1 squared is also going to be 1. Now to the next term, we're going to have 1, minus a -1. There we go. So this first bit right here is just 0, because we had to square that. So the -1 became 1. And so this becomes the integral of 2x dx. So when I integrate that, we're going to have x squared, again, from -1 to 1. And when I plug in 1 and I square it, I'm going to get 1. And when I plug in -1 and I square it, I'm going to get 1. So 1 minus 1, my final answer for this problem is going to be 0. All right. A lot of work to get 0, but yes, this is what you would want to show on a quiz or an exam or whatnot. Again, remember, if this is a standard response question, these are graded based on method, right? So you do want to showcase this method. Even if you got lucky and guessed 0, it's very possible that you'd get very few points on that. Just because, again, you need to showcase your method, what you learned in the calculus class. All right, well, I have another problem here for us. This one actually comes from an old final exam quite a while ago. So we have used Stokes' theorem to evaluate this, where S is the hemisphere. So this one, I think it's sometimes I ask students about this problem before showcasing the results or whatnot, or how to do this. And the thing that I notice quite a lot is that this right here is a very simple looking vector field. It's almost like deceptively simple looking, right? So this right here is our vector field F. And it is, in our first component, we have Y. We don't have any J's and we don't have any K's. So this right here is our vector field. And again, this bit is the curl of F. So this is saying to evaluate a surface integral of the curl of F. And that's why it's completely okay to use Stokes' theorem on this. Stokes' theorem says that instead of evaluating out this surface integral, right? I mean, if you were to just evaluate this out, I mean, that'd be wonderful and all that sort of stuff, but then you haven't used Stokes' theorem. Using Stokes' theorem means we want to go across the equal sign and swap this into a line integral, right? So in this case, because we're interested in evaluating out the surface integral, Stokes' theorem tells us that this is equivalent to evaluating out this line integral here. So we need to be interested in our surface, and in particular, its boundary curve. So right, the C here is the boundary of S. So when I see my surface S is the hemisphere, and it looks like the unit hemisphere, so that is the radius is 1, and we only have the top. So that's what the surface looks like, right? So this right here would be maybe S, our surface. But then if I'm interested in the boundary curve, this is again where the surface abruptly stops. So that's going to be down here where Z equals 0. So when Z equals 0, that's where it kind of abruptly stops. And that gives us our boundary curve. So by the way, if I was to go ahead and plug that in into my surface equation, Z equals 0, I would have x squared plus y squared equals 1. And again, this is when Z is equal to 0. This is important information because I'm going to need to parameterize this boundary curve, right? I'm going to need to figure out some R of t that helps describe this boundary curve. And so the fact that this is a circle of radius 1 in the xy plane, aka where Z is equal to 0, this is all very useful information. Okay, so let's remind ourselves that, right, when no orientation is given, we're assuming a positive orientation. That means that it's going to be pointing upwards or outwards. So, right, our normal vectors for this surface are going to be pointing upwards, something like this, or outwards. And if I was to draw a normal vector that's pretty close to our boundary here and think about the right-hand rule, I hope that everyone would agree with me that we're pushing the wiffle balls in this direction here as my fingers curl around that normal vector. And this has a counterclockwise orientation when viewed from above. So again, kind of a positive surface orientation gives us this positive, nice counterclockwise boundary curve orientation. All right, so if I wanted to parameterize this thing, I'm going to use the classic parameterization for a unit circle. And that is my x-coordinate is going to be r cosine theta. My y-coordinate is going to be r sine theta. And my z-coordinate, well, in this case, right, it's a circle that's in the xy plane, or z is equal to 0. So therefore, well, z is 0. Notice that instead of thetas, I decided to use the parameter t. This is typical, right, when we first did this back in 13.1 and when we do this here. So if I want to go around and get every point once, that means that I want my t's to range from 0 to 2 pi. All right, so then why don't we go ahead and start plugging some of this stuff in. So I'm going to end up doing a t integral here. That means my bounds are going to be from 0 to 2 pi. My f was y0, 0, but again, I'm trying to do a t integral here. So instead of y, I'm going to go ahead and plug in my parameterization for y. So that is sine of t. So sine of t, 0, 0. Dot product with dr, right? So this is where we need to take our derivative of our r vector back here. So the derivative of cosine is going to be negative sine. The derivative of sine is going to be cosine. And the derivative of 0 is still just 0. So evaluating out my dot product, I'm going to have negative sine squared t dt. Now remember, there's a nice power reduction formula, I believe, on our formula sheet and whatnot for sine squared. And it should remind you that sine squared is equivalent to 1/2, 1 minus cosine of 2t. Let's go ahead and maybe factor out some of these constants. So the negative 1/2 we'll take out. And why don't we go ahead, we'll try to integrate this as well then. So if I was to integrate 1 with respect to t, I'm just going to get t. And if I was trying to integrate cosine, right, we're going to get sine. And that 2 there means we're going to need this extra 1/2, right? That technically there's a small u substitution going on here. So now let's go ahead and plug in. Let's see, for t, if I was to plug in 2 pi and 0, subtract, we'd get something like this. And let's see, we also have our minus 1/2. And sine of 4 pi is going to be 0. And sine of 0 is going to be 0. So actually this part is just 0. So my final answer at the end of the day is negative pi. And so again, if we were asking, what does this mean? We found that this has something to do, remember these line integrals had something to do with work. So this vector field overall does not want the particles going around in this counterclockwise direction. It would much prefer them going around in this clockwise direction rather than in a counterclockwise direction. So that's kind of what this is telling us, is that where our vector field is working against us. All right. I hope you can see that, this one is considerably shorter than the last one, right? So this is more in line with what you should expect for like quizzes, exams, time settings, right? After all, this did come from a final exam a while ago. All right, let's go ahead, move on and try another problem. This too is an old exam question. This one has, again, some vector field and a interesting surface. So our interesting surface in this case is basically a can on its side. So it's made out of 2 parts, a cylinder, and that ranges from x is -1 to x being 1. And again, it's this just y squared plus z. So that's all the sides of the can, essentially. Notice that this equation here doesn't have any x's in it. So it's basically a circle in the yz plane that runs free in the x direction. So that's going to be all of this, the sides of the can here. Again, lots of circles in the yz plane, ranging from x equals -1, so that's going to be back here, all the way to x equals 1, that's going to be up here. All right, so that's all the sides of the can, and then we have the back side of the can, right? So it talks about that there's also a disk. That's where x is equal to -1, and we're filling in the inside. So that means we're kind of on the boundary of the circle. That'd be where we're equal to 1, and also on the inside. So that's all of this back stuff here. It's already kind of shaded in blue. Yeah, me shading it really doesn't do anything there. So it's just that back side of the can. So the first thing that we want to do, according to the statement of this problem, is to identify and parameterize the boundary curve of S with the correct orientation. So again, I like to think about the boundary curve. If I was like an ant crawling along the surface, how could I go from the outside of the surface to the inside of the surface, right? Or how could I basically flip sides? So the top side to the bottom side or something like this. So in this case, I think the only place where I could actually go from the outside to the inside is going to be along this rim right here. The backside has the bottom on the can, right? So I mean, we can't go from the outside to the inside along the back. If I was an ant, I mean, I could take this turn and kind of start walking along the backside of the can, sort of deal, but I couldn't get inside of the can. So, okay, the only place where we really have a boundary is where we have some of our surface missing, and that's going to be this front side here, which remember, this is where x is equal to 1. So this has something to do with x is equal to 1. And notice that we're going to be on this kind of on the boundary of this green piece, which was this bit here. So y squared plus z squared equals 1. And again, we're going to be where x is equal to 1. That's where we're going to have our boundary. So again, oops, y squared plus z squared is equal to 1. Okay, so if I was setting up a parameterization for this, I would think about, okay, we have x needs to be exclusively 1, and then I need to parameterize y's and z's so that they satisfy this y squared plus z squared equals 1. So this is kind of like, sine squared plus cosine squared equals 1. And so I'd probably do something along the lines of y being r sine of t, and I'm going to have z to kind of take place of x, how x normally would be anywhere, and have r cosine t, or r cosine theta. So something like this. And of course, if I want to go all the way around, I would have t ranging from 0 to 2 pi. Now, we need to worry a little bit about the orientation, right? Because this is kind of, right, a bit of a strange surface, kind of a can turned on its side, we need to worry about the orientation a little bit. And so again, without any phrases here to specify orientation, we assume that we have an outward orientation, a positive orientation. So we're going to have something along the lines of this. So outward for the can is these are going to be some sample normal vectors. And if I was to get a normal vector that's pretty close to my boundary here, and again, if I was to take my right hand and spin my fingers around here, it looks like I'm going to be pushing wiffle balls in this direction here, which is a bit strange because this looks like it is the clockwise direction when viewed from, really this is actually viewing from below, and that's kind of why we have this clockwise orientation. So when we look at it like this, we get a clockwise orientation, which is a bit strange. But again, that's why we have to check with these orientations. And we could check and make sure that this isn't just a fluke, right? If I go, for instance, maybe more near the bottom, and again, if I have my right hand with my thumb pointing in the direction of that normal vector, I think my fingers curl around in this direction. And so again, I'm going to be pushing wiffle balls kind of again in this clockwise direction. So yeah, I don't think that was a mistake. We are pushing these wiffle balls kind of in this clockwise direction. So I need to check my setup here and see if I actually have this going in this good clockwise direction or not. So the way that I'm going to do this is with a few test points. So I'm going to choose, for instance, maybe t equals 0 and t equals pi over 2 and see if I have the correct orientation. Because this isn't a standard circle, right? Standard circle is typically in the XY plane. This one's in the YZ plane. And so I had this take the place of X, which is a bit strange. So again, all of this needs to be tested to see if I'm headed in the right direction or not. So at t equals 0, I would have this point, let's see, 1, 0, 1. So again, I'm plugging in 0 everywhere I see a t for my parameterization. And so let's see, 1, 0, 1, that's going to be kind of up here. So 1 in the x direction, 0 in the y direction, 1 in the z direction. So kind of at the top of this. Let's go ahead and check at t equals pi over 2. So t equals pi over 2, I'm going to have what? 1, and sine of pi over 2 is going to be 1. Cosine of pi over 2 is going to be 0. So 1, 1, 0. So 1 in the x direction, 1 in the y direction, 0 in the z direction. So something like this. So I traveled from this point on the top to this point here in pi over 2, right? So in 90 degrees or whatnot. So yes, this does seem to be actually heading in the correct direction. So looks like I got a little bit lucky. Remember, if you want to change your orientation, you can apply a negative sign to one of the two of these. If you apply a negative sign to both, you'll actually switch it and switch it back. Or you can also swap these. So rather than y being sine, you could have y being cosine and vice versa. So this would be ways to change the orientation if you need, but this seems to be heading in the right direction. So I'm happy with that. And we can move on. So next up, we would like to evaluate out, surprise, surprise, right, a surface integral. So we're going to write this as an equivalent line integral and then evaluate. So this problem right here, it does even mention use Stokes' theorem. So the equivalent line integral that it's talking about is thanks to Stokes' theorem. So Stokes' theorem says that this surface integral of the curl of f can be traded in for f dot dr. So let's go ahead and start plugging in our specifics. So our vector field is xyz, the first component. Our second component was 2xy, and our third component was x squared y. Then we're going to need our r prime of t dt. And let's go ahead and start plugging in some of this stuff, right? So for our parameterization, we have this up here. And when we integrate, we have a t integral. So we're going to go from 0 to 2 pi. After all, that was with our parameterization, what it gave us. Instead of x, I'm going to go ahead and plug in x being what? 1. That's where, again, this is looking at our parameterization. Y is sine. Z is cosine. 2 times 1 times sine, and 1 squared times sine. Dot r prime of t. So taking the derivative of 1, we get 0. Taking the derivative of sine, we get cosine. And taking the derivative of cosine, we get negative sine. All right, now we have the hard bit done. Now let's go ahead and evaluate out our dot product. So let's see, 0 times anything is going to be 0. Then we're going to have what? 2 sine cosine. And then we're going to have what? Negative sine squared. So when we evaluate this bit here, we have a small u substitution where u is equal to sine typically. And so when we integrate just u, or really 2u, we get u squared. So again, u is equal to sine, du is equal to cosine. So this is really the integral of 2u, which gives us u squared. And so this is going to be sine squared t. And of course, you can double check, right? If you take the derivative of this, you should get back to where you started. So this we're going to evaluate from 0 to 2 pi. But as you can see from this, right, when you plug in either 2 pi or 0 into sine, you're going to be getting out 0. So this bit right here is just going to give us 0. This negative sine squared t, well, actually, we had just evaluated this back here. So you may remember we need to use this power reduction rule. And at the end of the day, if we follow all of these same steps, right, we're going to get the answer of negative pi. So again, all of these same steps, and we get negative pi. So our final answer at the end of the day is going to be 0 plus negative pi, or that's just going to give us the negative pi. I was just peeking at my notes here really quick, and I see that I didn't get the same answer as I did before my recording here. And so that's rather alarming. Ah, darn it. I found it. This x squared yz. You guys were probably yelling at the screen while I was doing this. X squared yz. So I forgot a z here. Oops. Sad. So that means that this is going to be sine cosine, which means that this is going to be negative sine squared cosine of t dt. And so sadly, yeah, this bit isn't correct. So we need to redo this. But actually, now this is actually maybe even a little bit easier than we did last time. So again, this is going to be a u substitution where a u is equal to sine. Du is going to be equal to cosine. So I should include my dt's. And so this just becomes the integral of negative u squared du. So when I integrate that, we're going to have negative 1/3 sine cubed of t, and again, evaluated from 0 to 2 pi. So again, when I integrate this, I get the negative 1/3 u cubed, and u was just sine. Well, just like before for this other one, when I plug in 2 pi into sine, or when I plug in 0 into sine, both of these give out 0. So actually, yeah, my answer at the end of the day here is just 0 minus 0. So a little bit more of a boring answer, but all right, now it's at least correct. So, all right, well, I do have one more problem for us for today. So let's go ahead and take a look at this one. I think this is a good one that maybe you should take 90 seconds, 2 minutes, try to see how far you can get on this one, and then maybe come back. So please try this problem out, see how far you can get, and then we'll talk about the results together. All right, let's start talking about this one together. I did not make it all the way through by any means, but I think this is a good place for us to start chatting. So in this problem, it does not say use Stokes' theorem, right? We could decide to evaluate out this line integral. The only problem is once I sketched out this picture, I noticed that this triangle that it talks about is made up of 3 different line segments. So each one of these would need to be parametrized, right? They would have their own r of t. So therefore, each one would have its own dr, right? The r prime of t sort of deal. And then we need to evaluate out 3 different line integrals. And that would be a bit time consuming. So it's not hard necessarily, but it would take up a decent amount of time. However, if we were to decide to use Stokes' theorem, the natural surface that we would attach to this boundary curve would just be shading this in. And so we'd have this kind of relatively flat surface, aka a plane. So we'd have this plane that contains the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. So then the question becomes, well, how do I find the equation for the plane that has these 3 points? And we used to do this all the time in 12.5. So we could do this in this very similar method as we did for 12.5, finding the normal vector and attaching it to one of these points, right? So again, completely fair game and reasonable thing to do. However, because these are all of the intercepts, so we have, right, the x-intercept where it crosses the x-axis is 1, 0, 0. And we have 0, 1, 0. That's where it crosses the y-axis. So another intercept. And then finally, where it crosses the z-axis, 0, 0, 1. We can actually make a quick theorem here about a fast way to come up for a plane equation when all the 3 points given are intercepts. And so in this case, you just divide by whatever those values were. So in this case, we have our a value was 1, our b value is 1, and our c value was 1. So rather boring. So therefore, our plane equation is just going to be given by x plus y plus z equals 1. So, and of course, we can double check, right? We can verify that 1, 0, 0 satisfies this plane equation, and 0, 1, 0 satisfies this plane equation, and 0, 0, 1 satisfies this plane equation. And therefore, this is a plane that contains these 3 points. All right, so a little bit of bonus information, a little bit of cheatery, I suppose, but um, this is a nice, fast way to come up with plane equations when you're given all intercepts. And with this, we can then start to evaluate out this surface integral of the curl of f dot ds, because now we have this, our surface equation. The other thing that we need is also this curl. So why don't we spend a little bit of time here calculating out the curl of f. So I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. And our vector field is z squared, y squared, and x. So stuff with i's minus stuff with j's plus stuff with k's. Crossing off that first row and first column, we have what? 0 minus 0. Crossing off that first row and second column, we have 1 minus 2z. And then finally, crossing off that first row and the third column, we have what? 0 minus 0. So this ends up being the vector 0, 2z minus 1, 0. So that right there is our curl. So if I was to go ahead and calculate out then and start to plug in, we'd have our curl. And then remember, we need to dot product with a normal vector, right? This ds has a normal vector. And so when I look at my surface equation here, I need to get this as a z equals. So z is equal to 1 minus x minus y. And then if I have a z equals, then the normal vector is going to be given by plus or minus. And in the first component, we have a partial derivative with respect to x. In our second component, we have a partial derivative with respect to y. And then in our third component, we always have -1. And I have to decide, am I happy with the normal vector as it stands, 0, -1, -1, -1, in which case I would just choose positive and leave it as is? Or would I like to flip my orientation and choose the negative here and distribute that to each piece? So, okay, well, I need to think about the orientation really quick. If I'm going around in this counterclockwise direction, if I was to go ahead and, again, with my right hand, have my fingers curl around in this direction, it seems to me that my thumb is kind of pointing out, kind of towards my face. So out of the page here towards my face. And so this seems to have like a positive X, Y, and Z component, right? It seems that in particular, I mean, it's kind of facing up for me personally. And so I think I'm going to choose the negative here and distribute that to each piece. And then I do have a positive X, a positive Y, and a positive Z. So I choose that extra negative so that way we have a normal vector with a positive Z component. So now that I've chosen my normal vector, let's go ahead and evaluate out this dot product. Oops, and I forgot apparently one component here, 0. So when I evaluate this out, what I get 2z minus 1. Now remember, I'm about to do an integral in like the xy plane. So, right, I really shouldn't have any z's at this point. I should only have x's and y's. But luckily, for my surface equation, I have an exchange rate, right? I know that z on my surface is equal to 1 minus x minus y. So I could go ahead and swap in, and everywhere I see a z, I could put 1 minus x minus y. All right, now I need to think about my bounds and whatnot. So I'm going to go ahead and take my surface here and smush it into the xy plane. So if I was to go ahead and take this and smush it down into the xy plane, I think the entire shadow or all of the residue or whatnot, it's kind of the surface smushed down in the xy plane, would still be with an x value of 1 or less and a y value of 1 or less, right? And it'd all be kind of smushed down here. So again, remember, here was the point where x was 1, here is the point where y was 1, and I've smushed this down into the xy plane. So it's everything kind of from the origin inside of this triangle with the x-intercept of 1 and y-intercept of 1. So something like this. So given that, if I was to integrate maybe with respect to y first, it seems like I enter in through y equals 0, and I exit through this slanty line. Well, this slanty line right here, maybe unsurprisingly, is when you take this plane equation, and if you've smushed this down into the xy plane, well, the xy plane has the equation z equals 0, and we could solve this and get that y is equal to 1 minus x. And of course, this line right here has an intercept of 1, and it has a slope of -1, right? It's headed down. So this y equals bound should be 1 minus x. The smallest x value is 0. The largest x value is 1. So this right here is going to be our setup. Let's go ahead and start to evaluate this. Take a line to distribute all this, right? So we have 2 minus 2x minus 2y, but then we need to subtract away the 1 there. So 2 minus 1 will be 1. Now let's go ahead and integrate this with respect to y. So I'm going to have what, y minus 2xy minus y squared. And oops, I need to evaluate that from 0 to 1 minus x. So I'm going to have what, 1 minus x minus 2x, 1 minus x minus 1 minus x quantity squared dx. All right. Well, we would need to now distribute this a little bit. In fact, this is a bit where if you were to rearrange this a little bit, this is where this hint ends up coming in, is that this integral here is meant to exactly match up with this. Again, we need to just distribute just a little bit. And so the final answer is going to end up being 1/6. So if you have a little bit of time, I recommend that you see this all the way through. But at this point, right, we're just solely back into calculus 1. We need to distribute this, spend a little bit of time with it. But we've done all the hard calculus 3 stuff. Again, the setting up of this integral and figuring out once we smush it down into the xy plane, what that looks like, right? Really, the setup is the hard thing here. All right. Well, I hope that you guys enjoyed. I hope that you're having a wonderful day. All the best of luck to you, and I will see you later.